Hello everyone, I'm Song-Min Park from Seoul National University Bundang Hospital. Now, I'd like to present an application of robotics in endoscopy.
Minimally invasive surgery has disadvantages, such as a steep learning curve, prolonged operative time, and increased radiation exposure. To address these issues, robots and navigation systems are increasingly being used in MIS procedures. Robotic assistance can enhance surgical precision and stability, reduce human errors and fatigue, and theoretically improve surgical safety. The most commonly used robotic system worldwide is the Vinci system. The surgeon controls the robot while viewing the screen from a console, making it a master-slave type robotic system. In previous research, there was a case report of anterior corpectomy performed using the Vinci system. Although I haven't performed it myself, soft tissue removal seems relatively straightforward, but I'm curious about how bone resection is accomplished. Recently, AR technology has been integrated into robotic systems. This is a paper on liver resection, where the tumor location is 3D reconstructed from CT and overlaid onto the robot system, allowing surgeons to visualize tumor positions that were previously invisible during surgery through AR. Unlike existing fields where robotic surgery is applied, spine surgery involves operating on skeletal muscle, bone, and neural tissue. Due to these differences, particularly bone, it's difficult to apply existing robotic surgery systems.
Therefore, spine robotics has developed in the direction of improving the accuracy of pedicle screws. It has evolved as an advancement of existing navigation systems. The robotic surgery method is very similar to existing navigation systems. It goes through planning and registration processes and then performs screw fixation. Recently, many pedicle screw insertion robotic tools have been developed and are being used, with similar operation methods and accuracy across different companies. According to previous research, the accuracy is higher in robot surgery than freehand and slightly higher than navigation surgery as well. The accuracy of robots is at a level where there's no difference between expert surgeons and residents, so even surgeons unfamiliar with the procedure can achieve relatively high accuracy in pedicle screw placement. When robotic systems are applied, considering operative time, revision, infection, and length of stay, cost-saving effects have been reported. This is a robot from China. This is also not specifically designed for endoscopy, but for screw positioning. They use the robot to position and stabilize the endoscope for PLD procedures. Compared to conventional PLD, they reported better results in puncture time, fluoroscopy time, and operative time, with C-arm-based robots showing the least fluoroscopy time. This is also a Chinese paper. It's the same surgery, but from a different Chinese robotic company, Sanrobo. Similar to the previous paper, it showed comparable results. This is also a Chinese paper. This time, it's about full endoscopic TLIF, where the robot arm similarly performs navigation and portal fixation for endoscopic TLIF. Robot arms seem to play a relatively good role in full endoscopic surgery. Next is a paper from Belgium. This is an ultrasound-guided navigation robot that automatically positions and stabilizes the endoscope with real-time correction capabilities. It generates anatomical structures based on CT, and the robot sets and maintains accurate surgical pathways, supporting surgeons to perform stable surgery. It's similar to existing screw insertion robots, but differs in using ultrasound for position adjustment. This is a robotic system being developed in China. It's being developed for transforaminal endoscopic foraminoplasty. Through preoperative planning, 3D modeling is performed to identify surgical pathways. Then the robot identifies surgical pathways in real time and automatically adjusts pathways using image recognition technology. It's described as a robot that uses multiple sensors to receive real-time haptic feedback while preventing neural damage and monitoring real-time status. Robotics is still in its early stages, and I believe there will be significant development in the future. Currently, it's only used for screw insertion, but I think it will likely be used for actual neural decompression as well. For accuracy improvement, registration and real-time tracking are necessary. For enhanced safety of neural tissue during surgery, 3D modeling, AR overlay, and surgical field recognition capabilities will be needed. For actual neural decompression, development into a master-slave type robot surgery system like Vinci will be necessary. Optical technology continues to develop and is expected to advance much further. Not only resolution, but also illumination development, moving cameras, and 3D visualization are all expected to progressively improve. Also, using burrs and punches during surgery causes surgeon fatigue. To address this, non-contact hard tissue cutting and drilling instruments such as lasers are being developed. Navigation systems are also advancing. Registration devices like O-arm are becoming smaller, and X-ray-based real-time tracking technology is being developed. X-ray-based real-time tracking technology is being developed to track each spinal segment without optical markers. AR technology is also being developed to overlay surgical plans, structures that must not be damaged, such as neural or vascular tissues, and surgical tools onto the surgical field. Methods for calculating optimal positions for pedicle screw fixation using AI technology have already been developed, and in the future, methods for calculating optimal surgical pathways and bone resection for procedures like decompression surgery are expected to be developed. When the various technologies I mentioned earlier are developed, I believe the following robot-assisted spine surgery system will be developed. Through a master-slave type surgical robot with multiple arms, less fatiguing surgery will be possible. Also, optimal surgery can be planned based on AI, and safe surgery can be performed through AR visualization. I believe surgical accuracy can be improved through real-time tracking using precision optical sensors and low-dose X-ray technology. Such robotic systems can be applied from surgical planning to surgery completion with advanced technology applicable to each stage of surgery, helping to perform accurate, safe, and convenient surgery. Let me show you the robot-assisted biportal endoscopic surgery that we're researching. It's a robotic device consisting of an endoscope arm and working arm. It's a master-slave type that can be controlled remotely. This is a phantom experiment video. The left hand controls the endoscope arm, and the right hand controls instruments like burrs. In the video, the right hand is controlling the endoscope burr. The actual burr movement is designed to be smaller than the right hand movement. We also did animal experiments afterward, but I'll skip those. Finally, this is a cadaver experiment video. We conducted experiments on cadavers using actual surgical instruments. First, this is a video of laminotomy using a burr. The cadaver bone wasn't particularly hard, so it cut relatively well. Next is the punch video. We implemented the punch, but it was quite difficult. We configured the robot arm with 6 axes, but since actual punches don't move in 6 axes, it was very challenging. For one portal endoscopy, it might be sufficient, but for biportal endoscopy, 6 axes is quite difficult. With only 6-axis movement, including up-down linear motion, rotation, and left-right movement, surgery was challenging. We also experimented with the Penfield dissector. We did test the dissector, but since subtle tactile sensation cannot be felt, it seemed only capable of basic dissector functions.
Robot-assisted systems are mostly developed for screw fixation, so for use in ESS, they're being used for navigation and camera arm stabilization. C-arm or X-ray-based robot systems and ultrasound-based robotic assistance systems are being developed, but much development is still needed. Ultimately, it's expected to develop into a complete master-slave type robotic surgery.
Thank you for listening.